All right, so this is going to be the first of a series of videos looking at numpy. So the goal of this video is just kind of to get a little bit of familiarity with numpy and the basic or kind of the core data type that is offered by numpy. And we're going to look at single dimensional arrays, just some of the basic functions on single dimensional arrays, just to kind of get, again, a little bit of familiarity with the library and kind of the basic type. All right, so the way that we would typically import numpy, so of course, if I'm working in Anaconda, so I've got a Conda environment created where I have installed numpy. So you would definitely need to have that if you're using just base Python. You know whatever your Python distribution is, you could do a pip install numpy, or if you're working in Anaconda, you're in an Anaconda environment or a Conda environment, and you could do a Conda install numpy, or you can install it from Conda Forge. But once you've got it installed, you can import numpy as follows. So this is kind of the typical way that people will import numpy. So we're going to say import numpy, and then we're going to give it this alias np. All right, so that's going to import the library, and just so that we're all kind of on the same page, I'm just going to show you the version that I'm using. So if you're running an older version of numpy or even a newer version, you know, after this video is created, just so that you know, this video was created with respect to numpy version 1.26.4. But a lot of the things that I'm gonna be looking at, again, are just very core functionality, core types in NumPy. So I don't anticipate this changing, even though there is, you know, talk at the moment that I'm recording this of NumPy going to a 2.0 release. But again, these are very much the kind of the core utilities in NumPy. So even if it does go to a different version, I do anticipate anything that I do here being compatible with that later version. All right, so NumPy is basically a library for numerical computing in Python. A lot of people kind of think of it as an alternative to MATLAB, and a lot of people that are familiar with MATLAB might see a lot of similarities with NumPy. And actually, the individual that wrote NumPy, you know, at the time he was doing, I think he was doing a PhD, and he was looking at coming up with some numerical capabilities for processing MRI data. And that was kind of what inspired it. So he had a MATLAB background, was looking for, you know, some utilities, some scientific computing capabilities in Python, and he started building NumPy, and it has kind of turned into one of the cornerstones, I would say, of the scientific computing ecosystem in Python. And really kind of the core data type that it implements is going to be what we call an ndarray. A lot of times we just refer to this shorthand as a numpy array. And let's see how we can create one of those, right? So first off, I'm just going to make a list. And let's see, let's do that. All right, so right now, if I were to run this and look at the type of this my list object, all right, that is a Python list. And if we want to convert this to a NumPy array, we can say np dot, and it has this array function. You can provide it a list. And now if I look at the type of this, we have a NumPy nd array. Now, the important thing to realize is this ND, that's standing for n-dimensional. So technically with NumPy, you can make multi-dimensional arrays. So single dimensional, you know, just one dimension, 2 dimensions, that would be like a matrix. Or you can have, you know, more than 2. So a common representation for images in Python is using a 3-dimensional NumPy array, where you have essentially a bunch of 2-dimensional grids that are representing pixels, and then you have that across 3 channels, like a red, green, and blue channel. All right, so now we have this NumPy array, and let's just print this out to the screen. All right, so you can see that it looks very similar to a list, and actually in this case we've created it from a list. So a lot of times either I'm working with a list, or if you're working with something like a pandas or a polars, they can you can actually use methods on those libraries that will take columns and send those directly to NumPy arrays. Or as we'll see in later videos in this series, you can randomly create arrays. So maybe arrays of random numbers, and that's actually a very common use case, at least for myself. All right, but for now we can use a list and we can convert that list to a numpy array. Again, in a future video, I'm going to do a head-to-head comparison of some list operations against a numpy array, and we'll see some significant advantages that it offers with respect to computational speed. And that is a big advantage of NumPy. So it handles things, you know, if I were to say, okay, well, why might I implement something in NumPy versus a list? Well, there's some nice things about it. So first off, a NumPy array, in this case, we have all integers in this array. So if I were to look at my array and then do dtype, let's say I think it's just dtype. There we go. So it enforces that within a particular array that we've got to have a consistent type. So as we've talked about in my Python fundamentals playlist, a list is a very flexible structure. So we can put all types of things here, but most of the time when you're working with a NumPy array, it's going to try to do some type of a conversion to a consistent type. And that kind of helps it as far as doing optimizations because it doesn't have to check the type of each element in that object. Now, I would encourage you when we're using NumPy, it is for numerical computing. So I would encourage you, this NumPy arrays are not going to be very suitable for handling string data. Even though I think you can force string data into a NumPy array, it's not built for that. It's built for numerical computation. But we do have a consistent type, and then also the way that it lays out, NumPy lays out arrays in memory on your machine, allows for much more efficient processing. So we can get some real speed benefits from doing that. All right, so we've seen how I've got a list. I can convert that to a NumPy array, and we've got this dtype where we can see what the data type is, and it will infer that from the data that you've passed. And then another very common method that's used a lot, so we can get the shape of a NumPy array. So in this case, we have this single dimensional NumPy array. So one dimension, so the way to think about this is it's a vector, right? So you can see how it's representing that vector. So it's saying, okay, well, this is a one-dimensional array. It has 5 elements in that array. So it's using this tuple, 5 comma. So that's the way that it's indicating that this is single dimensional with essentially 5 elements. All right. We could get similar information if we use the size attribute. All right, so this is telling us how many items we have in that NumPy array. So again, if I just look at the help of this, oh, so that's returning that int. So, all right, so let's see if I were to do my array.size, let's see. Yeah, we can't get the help function back on that size attribute because that is actually an attribute of that NumPy array. If we wanted to see the help on that, I think we could actually do the help of the array object itself, and it will probably show us the method. So there we go. So there's our size method, and that is going to be the number of elements in the array. All right, and it shows us a lot of other methods, so I'm going to scroll to the top. I know I'm hurting eyes here, but just note that if you've got a NumPy array and you wrap it in help, you can see a lot of information and documentation on all of those methods that are available. All right, so we know how to get the shape, and this is really helpful in us figuring out what's the dimensions, how many rows, how many columns, or the way that I want you to think about that in future videos is going to be the number of axes that your array object has, and then we can get the size, which is just telling us the number of elements. All right, so I want us to just look real quick. So we've got our array. Indexing on this single dimensional array is going to work essentially the same way as it would for a Python list. So if I wanted to grab that 2, that's right there, right? So if we remember, so indexing a list started from 0. So if I'm going to grab that 2, I can grab the 0 index item, and that gives me back my 2. All right. If I wanted to get this 5, that would be index position 0, 1, 2. So that gives me back that 5. So again, indexing is going to work very, very similar to a list. We'll actually see in a later video that slicing works very similar to a list as well. All right, but now that we've got this array, if I were to do a dot and hit tab, we can see that we've got a lot of different methods that we can call on this array. Most of them kind of related to either reshaping the array or some type of a mathematical operation. All right, for example, if I wanted to find the mean, the average value for the items that are in that array, I can call this dot mean, and it's going to say, well, the mean value is 3. All right. If I wanted to get the standard deviation of these, I can take this std method and I can get the standard deviation of those values. So now we can start to do computations, whereas before, if we were dealing with a Python list, it's just kind of this generic option, and we can actually see, because we have a list defined as my list, if I do a dot and then hit tab, we've got things that allow us to do operations on the list. But if we're going to do any type of mathematical operations, we're going to need to write custom functions ourselves to do those processes. Right, so numpy being a library for numerical computing, right? So on these array objects that it provides back to us, it's giving us various methods for mathematical computations. All right, now one thing I'm kind of brushing over at this point, because we're dealing with a single dimensional array, is if I were to go to like this std or even that mean function, I'm going to get inside those parentheses, hold down shift and hit tab. All right, you can see that there's arguments, right? So we've got arguments that we can pass through these methods, and these are going to depend largely on the method that you're using. But one that's going to be fairly consistent is this notion of an axis. Okay, so we'll see that in future videos, but the way to kind of think about it, so we're dealing with this n-dimensional array, and the axes kind of correspond to which dimension are you doing these operations on. So in addition to just allowing you to do mathematical operations, you can actually kind of specify to numpy that when you do these operations, you want to do it over certain dimensions of your array. So just wanted to kind of go ahead and get your mind primed to think about that. All right, so again, we can do things like just showing you a few of the common ones. We've got a sum. All right, so if we wanted to take the sum of those elements, so 2 plus 1 is 3, plus 5 is 8, plus 4 is 12, plus 3 is 15. All right, and we can actually do a cumulative sum. All right, so a lot of different things that you can do just kind of right out of the hood. So you can see what this cumulative sum is doing. So if we think about left to right in this array, well, the cumulative sum through this element here is just 2. And then the Q sum through these two elements, right, the 2 plus 1 would give us the 3. 2, 1, 5, that's going to give us 8, and so forth. So it's essentially accumulating the sum of these items across, in this case, the only axis that we have in this array. All right, so just a few other things as far as functions that I wanted to show you, or at least functions doing computation that I end up using quite a bit. So if we take my array, again, just to show you what that looks like, and we can find the minimum and the maximum values. All right, so if I say my array, and I say give me the minimum value, it's just a dot min. It says, hey, the minimum value that I encountered in this array is a 1. But here's another interesting take on that minimum that can be very, very helpful in many cases. So sometimes we don't want to know just what is that minimum value, but we want to know, okay, well, at what index position does that minimum value occur? All right, so what you can do, in addition to min, you have an arg min. All right, and what this is actually doing, it looks like it's giving you the same thing because min gave me 1 and arg min gave me 1. It's actually saying, oh, it looks like they're doing the same thing, but what this argmin function is actually doing is it's saying, hey, okay, the argument, the index position where that minimum value occurs is the index 1 position. So 0, remember, that's your 0 index, and then that's your 1 index. So it says the value 1 is essentially occurring in that second position, or your index position 1. All right, we can also do this with max. All right, so if I want to find the maximum value, we can do my array.max, and then equivalently there is an arg max. All right, so in this case, the maximum value is 5, which occurs in index position 0, 1, 2, and that's exactly the value that is returned in when we make that argmax call. All right, so just a couple of other things I wanted to show you. So sometimes you will work with libraries, like in this case, we're dealing with a single dimensional array, and we could see that if we do this shape. But sometimes you'll be working with libraries. So a lot of libraries out there work very well with NumPy. They actually expect NumPy arrays for various arguments, or do a conversion to a NumPy array if they don't explicitly require you to pass one. And sometimes they might require you to do some reshaping of your array. And this is particularly, I encounter this case a lot when I'm dealing with vectors. So in this case, we got a single dimensional array. Well, it could be that, especially in like machine learning libraries, I'm thinking of stuff like scikit-learn. It expects this to be maybe, a single row. And then to explicitly have, the array shape so it's one row and, say, in this case, 5 columns. Or it might be expecting a column vector where you've got, in this case, 5 rows of a single column. So, knowing how to kind of reshape an array that you have is actually really, really handy. And what I'm going to show you, so let me actually define a slightly different array for this demonstration. So I'm going to go up here and I'm going to get, so I'm going to say my array, that's going to be equal to an np array, and then let's just do 1, 2, 3, 4, 5, 6. All right, so now I've just redefined my array. Okay, if I do the shape, it's going to be a 6-dimensional array. So it's just, single dimension, right? But it's got 6 elements, I should say. So it's like a 6-element column or a vector in NumPy. All right, so what if we needed to reshape this to where there was explicitly one row, 6 values? So think of it as like a row vector. So it's got, explicitly one row and 6 column positions. Again, we're going to talk about in another video this notion of broadcasting of arrays. And this is exactly the type of situation where you would need to do something like that when you're trying to broadcast to another array, which basically means I can take an array of one shape in NumPy if I'm trying to perform an operation that maybe combines 2 arrays in some way. If the dimensions are mismatched, so they're not exactly the same dimension, what NumPy can do is it can look at the dimensions of one array and figure out how it could apply that to other dimensions. And again, more details on that to follow. For now, we're just looking at how we can reshape. All right, and there is a handy reshape function. All right, so if I look at the arguments of this, reshape, it just takes a shape parameter and then this order C, which you should not have to worry about. And you can kind of see some of these arguments, right? So you can actually, pass in, so it says, unlike the free function, numpy reshape, this method allows the elements of the shape parameter to be passed as separate arguments, right? So you can either pass it as a tuple, or you can pass in the arguments in separate arguments. So we'll look at both of those cases. So right now I've got 6 elements in this array. What if I wanted to reshape this so that this array had 2 rows of 3 columns? All right, well, one way that we could specify that is that, right? So we specify that rows element first and then our columns. And again, the way I want you to start thinking about these instead of rows and columns is axis 0 and then axis 1, right? So the 0 axis, that's capturing our rows here, and the 1 axis is capturing our columns. And this will be helpful not just for NumPy, but also for pandas, which is built on top of NumPy. All right, so in this case, I did a reshape of 2, 3. And what that function, when I was looking at that definition and it was talking about, for example, these two are equivalent, all that means is I could also do that reshape as follows, just taking out those inner parentheses, which would represent a tuple, and I can just pass the arguments in separately, and we get a 2 by 3 array, right? So if I were to do my array reshape 2, 3, and call shape on that, we get a 2 by 3 array. Now, what I'm doing here is actually really subtle. You probably didn't pick up the significance of that, but notice that when I call this dot shape, what I'm essentially doing is I've taken an array with my array, and then I called reshape on it, and the thing that it returns to me, right? So if I take that shape off, that's actually a NumPy array, right? So if I check the type of what the reshape returned, that's actually another NumPy ND array. Okay, well, since I know that that's returning an array, well, we've already seen that NumPy arrays have a shape attribute. So that's why I can call shape right at the end. So I'm just chaining those calls right on the end because I understand the type of the thing that's being returned. So again, it's very important for you to kind of learn types, understand types, and kind of keep a mental note of types as you go along. All right. So we could do the reshape as does if we wanted to make it, where there's like 3 rows. So axis 0 has 3, elements there. And then 2 columns, so axis 1, we could just change that, right? So I want to have 3 and 2, and there we go. All right, now of course, I've got 6 elements in that original myArray object. So if I try to do a reshape into something that is not compatible with those 6 elements, it's going to have a problem, right? So if we did a reshape and I tried to make it 2 rows, 2 columns, well, it's going to tell me, hey, you can't do that. You've got 6 elements, you've got size of 6 on that original array, and you're trying to reshape it into 2 by 2. So that is an incompatible size. And if we tried to do something like 3 by 3, right, that's not going to work. But we could do something like 1, 2 by 3, right? So notice right here the difference between, let's just show this, right? So when I did 2 by 3, all right, these two things look pretty much the same, but the key thing to note is right here. So at the beginning of the start of that array, I've got 2 pair of those brackets, right? So here's my first row, second row, and then here I've got essentially 3 pair, right? So if I were to save this thing as X, well, now if I do X.shape, all right, so that's the shape. It's got 1 dimension in axis 0, 2 dimensions in axis 2, and 3 dimensions in axis, 1 dimension in axis 0, 2 dimensions in axis 1, and 3 in axis 2, right? So if I wanted to grab, maybe this 5 right here, okay, I would, need to first get into axis 0 and then do the, manipulation to get to that 5, which would be, so if we think about this as a list, so I've gotten into axis 0, all right, and now, so this is a 2-dimensional array. So what I need to do is I need to get that second, essentially row there. So I'm going to say, well, give me back index position 1. That gives me back that single dimensional vector. And then if I want to grab that 5, that's 0, 1, that's in the 1 index position. And we can grab it like that. So that's how we would grab it if it were a nested list. In NumPy, you also have the flexibility of doing things like this. We don't have to have separate braces. We can just put them all in a single brace. So index 0 in axis 0, index 1 in axis 1, and index 1 in axis 2, and we can grab that 5. All right, so we've seen how we can do reshaping and it can be compatible, but let's say that I've got this array. All right, and again, I want to just make it so right now that shape, if I were to look at that, all right, so it's a single dimensional vector, essentially, or array with 6 elements in it. If I wanted to make this explicitly like a row vector, so it's got, a single row and 6 columns, what we could do is we can use this reshape with negative arguments. All right, so I can say, well, you know what, give me 1 row, all right, one index in axis 0, right? So just essentially 1 dimension there. And then give me as many as you need in that axis 1. So give me 1 dimension in axis 0 and as many as you need in axis 1. All right, so notice now what's different. So remember, originally this is what my array looks like. All right, so you can just see it's a single, just a vector. Notice it's got 1 brace at the left and 1 at the right. And then when we do this reshape, it's got 2. All right, now again, this is returning a NumPy array, so I can check the shape of that. All right, now it's explicitly 1, essentially 1 index in axis 0, and then we got 6 in axis 1, as compared to this notation right here, which just said, well, this is a 6-dimensional object. All right, now similarly, if we wanted to get in this case, 6, entries in axis 0 or 6 rows, and just one index in axis 1 or one column, we could do a reshape. And we could say, you know what? Give me as many index positions in axis 0 as you need, but only give me one in axis 1. And now you've got, looks like a column, right? So now if I grab that shape, all right, so essentially 6 positions in axis 0 and 1 in axis 1. All right, so let's just kind of, close up by just looking at, a couple of things. So we've been working with single dimensional arrays, and just to kind of show you another thing and kind of maybe whet the appetite for what's to come, let's just look at like a simple operation. And again, this will kind of reinforce that notion of understanding your types and maybe some of the efficiency, at least from writing code, that NumPy will give you. So I'm going to make 2 NumPy arrays. So let's do 1, 2, 3, 4, 5. Right, and then my array 2, and let's do NumPy array, let's say 6, 7, 8, 9, and then we'll do 10. All right, so let's think of a very common operation. So those of you that are familiar with Excel, you are certainly familiar with the sum product function, right? So let's say that we've got 2 arrays and we want to compute a sum product of these 2. All right, so first off, let's just do this raw. So what if we were manually kind of putting these things in? All right, so it would be 1 times 6 plus 2 times 7 plus 3 times 8 plus 4 times 9 plus, in this case, 5 times 10. That's going to compute our sum product of 130. All right. Now, before we show the NumPy equivalent, I'm going to write this out using Python list. So I'm going to call this my list 1 and then my list 2. And those are just going to be list objects of the same entries that we put in for our NumPy arrays right here. All right. So let's see how we might do a sum product in just pure Python with lists. So what I might do is I would say, because we can't just, multiply lists together. So that's not defined for Python lists. So what we actually need to do is do a loop. So I would maybe make a sum product variable equal to 0. And I might use like the zip function. So I might say for val1, val2 in zip my list 1 and my list 2. And for each combination of those values, I'm going to say sum product plus equals, and that's going to be val1 times val2. All right, so I've got the sum product equal to 0. I iterate through the pairs of values in my list. Each time I'm multiplying the 2 values together and then adding that to my sum product. All right. So we compute that, and then it's 130, right, as we expected, because we went through and did this manually. All right, but let's think about how we could do this with an array. So what we essentially need to do, right, is we need to multiply the values in our 2 arrays. So we've got my array 1 and my array 2, and I'm just going to recopy them down here just so it's right where we need it. All right, so I need to multiply the values in an element-wise fashion and then just sum all of those products together. All right, so with NumPy arrays, what you can actually do, and this is a really nice thing, and this is kind of, when I was talking about this reshape, I was talking about, well, what if you need to do computations that involve 2 arrays, but up to that point, we had not seen them. So, at this point, let's see how we could do this. Well, this is very nice if we have, in this case, we've got 2 NumPy arrays of the same dimension, so they're essentially just vectors with 5 elements. So what we can do is we can actually just multiply those together, right? And what it's going to do is it's going to do the pairwise product of the elements in those 2 arrays. So we can see we get a 6 here from the multiplication of 1 and 6. We get the 14 here from the multiplication of 2 and 7. We get the 24 here from the multiplication of 3 and 8, and so forth. All right, so we've got, handled that multiplication, right, for all pairs in one go. And here's the key thing, right? notice what's the type of the thing that this is returning. So when I run this computation, it's returning something to me, right? Well, what's the type of that thing? All right, well, the type of that is a numpy array. So we're multiplying those two arrays, and it's returning to me another numpy array where the elements contain those products. All right, well, since that's a numpy array, right, if I'm going to just wrap this thing in parentheses indicating to do that computation first, right, well, that's the same object, right? It's a numpy array. So I'm saying, okay, put in parentheses, do those computations. And then remember earlier we saw that if you have a numpy array, you can do a dot sum, and that will sum all the elements up, right? So here's our products, right? This piece right here, val1 times val2, and we just need to sum them all up together to get our sum product. So now we can just call a dot sum, and there's your sum product. All right, so we went from this type of syntax where we're having to do looping using Python and Python structures to now we can come up with this succinct statement, which is to me arguably, even more readable than we had with this right here. So of course you can go through and really dissect this loop, but it's more variable names, it's more syntax. We're having to use the zip here, whereas here I'm just saying, okay, we'll take these two arrays and multiply them and then sum those things up, right? So we can come up with very readable expressions. And then, just to see right now, we're going to do a much more thorough job of this in the future, but let's look at, computation time. So notice right here, this code block is just doing that, that product using those lists, and I'm actually going to take out the print statement, and this one's doing the same thing using numpy arrays. I'm just going to put a time it right at the beginning of that cell. So double parentheses, time it, let it run that. So that takes 221 nanoseconds. And then if I were to do the same thing right here, looks like it's taking longer, but I think it's taking doing quite a few more loops. So let's see. All right, so we've got, in this case, 221 nanoseconds versus microseconds right here. So in this case, the Python list, it looks like is winning out, but we'll see very quickly that that story is not going to be the same once we expand things out. So in this case, even though we've got a more succinct expression, it looks like, the additional NumPy baggage has slowed us down a little bit. But again, we're going to have a future video where we do some very comprehensive comparisons of NumPy operations versus pure Python operations, and we'll see that this story is not going to hold, right? So a lot of times in this case, I think what is driving it is we're using really, really small objects, right? So we've got very, very small lists and arrays, but once we expand that out and we talk about arrays with, hundreds or even thousands of elements in them, it's going to be quite significant differences in the favor of NumPy. All right, so that's going to conclude this first video, and then in a subsequent video, we are going to just do some of these basics on a multi-dimensional array.